All right, looks like we've got a pretty good number of folks in here, so we'll go ahead and get started. Just like to say good morning, everyone. My name is McCain Vogel. I'm one of the assistant editors here with No Till Farmer. Thanks for joining us today for the webinar titled How to Reduce Your Fertilizer by Up to 70% While Increasing Yield, sponsored by Advancing Eco Agriculture, AEA. The discussion is going to feature AEA's Director of Applied Agronomy, David Miller, as he describes how to manage soil biology to release nutrients that are tied up in the soil mineral matrix and don't show up on a conventional soil test. So that's just a little preview of what you'll learn today. Before we get started with the presentation, just a couple of housekeeping items for you. As usual, on your screen, there's a Q&A icon at the bottom. You should see it there, and you can use that to submit questions throughout. And then we'll go ahead and wait till the end to get to those. We'll get to them at the end, as many as we can, many as we have time for. And then just a reminder that we're also recording today's session. So in the event you want to go back and watch it later or share it with anyone afterwards, you should get that sent to your email within about 48 hours of the conclusion today. So just look out for that. And without further ado, I'll hand it over to David.
Thank you, McCain. Hi, friends, and welcome to the webinar on how to reduce fertilizers and increase yield. I've worked with many hundreds of growers in the past decade, since 2008, when I first got into regenerative agriculture, started working with John Kempf, working with growers to reduce pest susceptibility, disease issues, address quality challenges, yield loss. And it's been a lot of fun and very rewarding as a consultant to team up with growers and solve these challenges that continually come up with growers. So it's been a lot of fun to see how applying these principles of regenerative agriculture and focusing on plant nutrition balancing the whole ecosystem and working with nature, we've been able to do so many exciting things, like prevent boll drop in cotton was a big one. Head scab in wheat is one that we did and had a lot of fun with. Spider mites in corn, to fruit split in cherries, eliminating the need for fungicide and reducing fungicides in a lot of different crops. And in a couple of crops, we were able to completely eliminate some of those tools by simply looking at plant health, focusing on plant nutrition. And one of the most common things that we find in these challenging environments, or when we start teaming up with a grower to figure out what is the root cause and what is the biggest limiting factor that is holding a grower back from reaching his goals, we often find that excessive rates of soluble nitrogen fertilizer, sometimes potassium and phosphorus fertilizer, and then also misaligned timing on the applications of those fertilizers are often one of the things that we look at and find that the reason we're seeing these challenges has to do with the imbalance of those minerals. So some of the things we're going to talk about today are going to be applicable for every grower. Other things will need to be adapted to your unique operation and figure out where you are as far as your soil health, as far as what's in your soil, et cetera, et cetera. So one of the things that's very unique to your operation, to what you're doing, is the whole idea of reducing fertilizer. And you may ask the question, is it really possible to reduce my fertilizer by 70% and maintain or increase yields? Well, yeah, I've seen it reduced as much as 100% and yields maintained or increased. But there's so much context. There's so many things that go into that. So whether it's 20%, whether it's 70%, whether it's 100%, the idea of the conversation today is to empower you with the knowledge and the understanding to team up with you, if you would like, to be able to understand how you can best invest your dollars that are going to give you the best return short-term and long-term. So with that, let's roll right into it. We can get this to work. All right. So a quick overview. We're going to look at understanding the fertilizers that you buy. So if you're going to reduce the fertilizer that you buy, by understanding what that fertilizer is, it really helps you to understand how you're able to reduce it without fearing significant yield losses. We're going to look at understanding your soils, especially your soil samples, what they tell you and what they don't tell you. And then we'll look at and just think about the carbon, water, and nutrient cycle, which is, we won't have time to really do that justice. we could talk all day about that, and I look forward to having more conversations, more webinars around that. But it is really significant, that whole cycle of the water, the nutrients, and the carbon. So your fertilizer, your crops that you're growing, whatever crops you're growing, and this is the challenge of a webinar, as nice as it is to have this conversation and to share these thoughts. I much prefer to be in the same room where we can have interaction, but that's not what we have today. So if you're growing corn, if you're growing wheat, if you're growing cotton, should you use a 20-20 fertilizer? Should you use a 10-10 fertilizer? What's the difference between a 20-20-20 and a 10-10-10? Maybe you should use a 20.500, or what if 8024, like a big number at the end and no zero in the middle? Maybe that's right. Or maybe you should use a 10-20-10 where you have a bigger number in the middle. Or maybe you should not have any. Maybe it should be a 00 with a 4 at the end. How do you know? Do you understand what these fertilizer labels and these numbers are? Or are you expecting someone to just tell you you need to buy this? And that's okay. But I want to give you the ability to ask some questions today by understanding what these numbers mean. And this is very much 101. So if you know all of this and it's way beyond, I apologize for that, but I feel it's very important to lay this foundation and understand what this fertilizer is that we are applying to the soil and what we expect to get from it, and why in some scenarios we're not getting what we expected, and maybe it's even detracting. So your first number is always going to be nitrogen. Your second number is always phosphorus, and your third number is always potassium. So a higher number of any of those three is going to indicate that you have a higher concentration of that specific element in the bag of fertilizer that you're buying or applying. So if you put out 100 pounds of 1152-0, known as MAP or monoammonium phosphate, how much phosphorus are you really applying? You're going to be applying 11 pounds of nitrogen, and phosphorus is going to be 52 pounds, right? No, not right. For some reason that nobody knows, nobody's been able to tell me. I had one older gentleman who owned a laboratory tell me he believes that the reason they're still going with this number, this way of measuring fertilizer, is because it gives you a higher number. If they go with the lower number, maybe growers wouldn't buy as much, or they wouldn't. They were afraid they would lose fertilizer sales. So 52, or the phosphorus number, is actually P2O5, not actual phosphorus. What does that mean? So if you apply 100 pounds of MAP, it'll give you 52 pounds of P2O5, of which 44% is phosphorus. So at 100 pounds, you're going to end up with 22 pounds of actual phosphorus. MAP is one of the most available forms of water-soluble or simple ion phosphorus that I know of. And doing some research, the highest number on percentage of plant absorption of applied phosphorus in the first season was 25%. So 25% of the 22 pounds of actual phosphorus is what you could expect your plants to take up in the first season at best. So that's 5.5 pounds of phosphorus that you're putting out for your crop. So what are you spending per ton for 11-52-0? What is that costing you per acre? And how much phosphorus are you really getting? 22 pounds of total phosphorus in 100 pounds of MAP, of which at the best you're going to get 5.5 pounds of that taken up by the plant. At worst, you might get very little taken up. And a lot of that is dependent on the amount of available calcium that you have, because this phosphorus in these soluble forms has been denatured through various chemistry interactions that have broken the naturally occurring calcium triphosphate bond. So in nature, as this phosphorus is mined, the raw ingredient that these phosphorus products are started out with is tricalcium phosphate, meaning you have calcium attached to this phosphorus ion. And so through this chemistry process, the phosphorus and the calcium are separated, the calcium is taken out, and the phosphorus is reacted with a nitrogen source and is very, very loosely attached to that, meaning it's very reactive. And for any of you growers who have ever made the mistake or accidentally put soluble phosphorus with calcium, you know what I'm talking about. You get an immediate, instant reaction. You get this gelling up. And when you put the soluble phosphorus out in your soil, like say in your pop-up or as a broadcast, you are effectively tying up the available calcium that was in your soil. And so now your fertilizer program doesn't have very much calcium and may be tying up the available calcium that you had, and therefore this phosphorus fertilizer could actually be a detractor in your overall system and your overall nutrient availability to your plant because of it tying up calcium in the process. What about the last number? What about potassium? That also is not potassium, but is K2O. Now, MAP doesn't have any potassium. As we can see, there's a 0, 11-52-0. So for that reason, I chose to go with potash. So we have 0 nitrogen, 0 phosphate, and we have 62% K2O. Now, that means there are 2 potassium ions for each oxygen ion in this molecule of potassium. So it's very interesting how this is even measured, because you have this K2O as a measurement, but in potash it's not even an oxide that, and yet it's reported in that K2O formula. So very complex, doesn't make any sense. It hasn't ever been changed. Nobody knows why, and I'm not going to change it today. Just letting you know what's happening. So if you apply 100 pounds of fertilizer with 62% or 62 as your third digit on your fertilizer label, that means you're applying 62% K2O, which means that you are getting 51 pounds of elemental potassium. And in potassium chloride or potash, you're getting 45 to 47 pounds per 100 pounds of chloride, which is one of the reasons why we always recommend growers who are wanting to transition to a more regenerative system and look at the whole ecosystem and environment and affect change in a macro way. One of the easiest things you can do is switch potassium chloride for potassium sulfate. Sulfate is an element that plants need and is often deficient because it's an anion. And so it needs to be applied on a more frequent basis, just like we think of nitrogen being, leaching, and we need to replenish the nitrogen. Sulfur needs to be replenished also because it's an anion, is not attracted to the clay colloid. And if we don't have organic matter or carbon or humic substances, we won't have an anion exchange capacity. So therefore, sulfur is going to be more likely to leach. So just switching from 0062 to 0050 or potassium sulfate will give you a much better response for your dollar spent. And you'll get about 41 pounds of potassium instead of 51 pounds, so 10 pounds difference. And now I'd like to also talk about the nitrogen piece, because nitrogen is something that has puzzled, in fact, perplexed me quite a bit to think about how much nitrogen gets sold in the agriculture industry. And yet when we look at the nitrogen cycle and when we understand nitrogen in a macro level, the way it operates in nature, we have this whole pool of the atmospheric gas is 78% nitrogen. And so nitrogen, as we know it in the fertilizer form, must first be processed through a factory. And I'll share with you in just a little bit how that happens. And then it's applied to the soil. And then from the soil, the plant will take it up directly, or it'll go through a nitrification process, and the plant will take it up as nitrate. And this particular diagram is a bit out of date because it's not showing the rhizophagy cycle, the possibility for plants to take up nutrients in a form other than nitrate. As we know it now, based on the work by James White, the rhizophagy cycle allows the plant to take up protein forms of nitrogen as well as even microbial bodies, and stripping the bacteria then of the various forms of nitrogen. So that's not the point of the conversation today, and yet it's very important to understand when we think about fertilizer or the nutrient cycle, and we think about how we supply our crops with nitrogen. So when you look at the nitrogen on your bag, when you're making the plans for how much nitrogen should you be applying on your wheat crop, your corn crop, your cotton crop, et cetera, whatever crop you're growing, why are you applying the nitrogen that you're applying? If we go back to this cycle, as you can see, the plants have the ability to fix nitrogen directly from the atmosphere and make it available to the plant through bacterial nitrification process. It's amazing how nitrogen has become such a significant part of our industry. And if you want to understand that more and dig into it, I did a webinar, I think it was the end of 2022. I should have written down the name of it. I don't remember now, but I shared there about how it was basically an outline of the history of agriculture and how we have what happened. I believe more by not understanding than by design that these applications of nitrogen came about and were so destructive to the whole system. So when nitrogen is fixed from the atmosphere in the factory so that you can then put it in your sprayer or broadcast it on your fields, there's a technique called the Haber-Bosch technique, established or came up or was developed in 1914, and then after World War II during World War II became very widely used. But the amount of resources that it takes to convert the N2 gas into nitrogen that we're able to use is tremendous. 500 degrees Celsius under pressure of several hundred atmospheres. It's amazing. Astounding the amount of resources that are needed to make this nitrogen that we're so used to, so dependent on. Excuse me one second. Sorry about that. You've all probably seen, a nice thunder shower, and it looks like the corn just grows. Well, that's because a thunderstorm will actually fix some nitrogen. The heat and the force that lightning puts out will actually break some of those N2 gas molecules and will fix some nitrogen. But activating the enzyme nitronase, which is used by the nitrogen or excreted by the nitrogen-fixing bacteria, can accomplish the same thing at ordinary temperatures and pressures. Like there's no, it's just a matter of, that's what they do, is take the nitrogen from the atmosphere, convert it into a plant usable form, and it just works. However, in order for that to work, we must have gas exchange. So the atmospheric gas needs to be able to go down through the soil, come into contact with these nitrogen-fixing bacteria, and then they can do their magic of converting that N2 gas into plant usable forms, and the plants grow. And we see this all around us in nature, where nobody applies any nitrogen and the trees grow and produce abundantly. So why do we apply fertilizers? If phosphorus fertilizer is, well, maybe even a draw, we have plenty of nitrogen out there, and potassium, yeah, well, maybe we need potassium, or do we? Why do you apply fertilizer? Maybe it is because you want to maintain the crop removal rates. And again, back to that nitrogen, the nitrogen that we have in the atmosphere, the nitrogen cycle. Nitrogen is usually one of the bigger ones that we talk about, or that gets lifted up when the crop removal rate is talked about. And it is, when you look at overall crop removal rate and you look at the protein levels and the nitrogen that goes out with the crop, yes, it probably is the highest crop removal. But it also is a resource that is replenishable based on what? I mean, what's the end of the amount of N2 gas in the atmosphere and that whole nitrogen cycle? How do we capture more of that? And how is it that we're not talking about calcium or magnesium? And there's more and more of that as this regenerative movement has continued to pick up steam, and people are becoming aware of the importance of all these other nutrients. But many times when fertilizers are applied, the focus is on N, P, and K, not on calcium, not on magnesium, not on the micronutrients. And when I think about a diet for me, I certainly want food that is more than N, P, and K. Maybe we're applying fertilizers because we have low levels in the soil sample, and there's good reason to apply when we have low levels in the soil sample. Maybe we're looking to increase yields, and I would just suggest that the only way that applying fertilizer will increase yields is if it's reducing some kind of stress that would keep the yield from being lost, because yields are at their highest potential when you plant. We don't plant and then increase yields. We plant and then we work to keep yields from being lost. So if your fertilizer is addressing a limiting factor that's stressing the plant, then yes, you will probably have higher yields than the control. Maybe someone just said you should apply it. Maybe it's something that you've always done on your farm. Maybe you've never asked the question, and that's okay too. That's part of why we have the discussion here today, is simply to say, never thought about that. Well, let's think about it. Let's see if we can understand why we do what we're doing. So here I'm showing you a soil sample, because this is a big part of understanding if you should be applying fertilizer or not, if you're going to have a benefit from applying fertilizer or not. So on this soil sample, I want to specifically point out the potassium level, the magnesium level, and the calcium level. And then also the manganese level here at 3. And now this next test is not it. The one previously here, I'm sorry, was an ammonium acetate extraction. So that's the MELEC3 and the ammonium acetate extractions are very similar in the amount of nutrients that they will extract. So they're comparable in that way. And now this next test that I'm showing you is a saturated paste analysis, which is simply a water that using deionized water and extracting what's in the soil solution. So it's just saying, what can my plants get very, very easily without any microbial and or chemistry interactions in order for with the what's on the ammonium acetate extraction. So if you remember, we had calcium at 939, and here we have it at 19. So there's a lot of calcium out there that's not available. So just because it's out here on your regular soil analysis does not mean that your plant is going to be able to access it, or that you're going to have advantage or get use or have enough. So we can't look at just one soil sample and say, oh, we're not going to, or we're going to have enough, if we don't understand the context of what's available because of microbial interaction and because of chemistry balance. And then if we look at the manganese, you can see that on this saturated paste analysis, where we had 3 parts per million, we have none detect, less than 0.02. And now I want to bring in the soil sample and that very few people look at. Something that we've only been looking at for a couple of years. I think it's probably 3 or 4 years since I saw the first total nutrient digestion report. And what this does is it's a much stronger extraction than the ammonium acetate extraction, and it will extract everything that's in the soil as far as minerals go. So the soil where we had 939 parts per million of calcium actually has 1,873 parts per million of calcium in the total soil matrix. But when we use a less acidic, or maybe more like what the plant roots might be excreting, and I will say the ammonium acetate and malic 3 those were established by William Albrecht. It's a very, very old way of looking at nutrient balance. Now we can see that, well, actually 939 parts per million of calcium, we probably, we don't really need any calcium because we have twice the amount here. If you look at the potassium, though, you see that we only have 86 parts per million total. And we want at least 125 parts per million in the ammonium acetate extraction to grow a good crop. So we have 81. And here we only have 86. So that is telling me we have 5 parts per million in the reserves, if you will, which doesn't sound good. Now, if we continue, you can see that we have the manganese. We have 23 parts per million in the total nutrient assay. So we had 3 on the regular soil analysis. We had 23 on the total analysis, and we have none detect. So we don't have any manganese available. We have a little bit on the regular soil analysis, and we have sufficient levels, but not an abundant supply of manganese in the total reserve of our soil. And when we, so here you can just see all 3 of them. You have what's in the regular soil analysis. And if you're looking at potassium, you can see that there's not enough nutrients here to really bring these levels up to the desired value. So it would make sense in this case to apply some potassium fertilizer. Now, when we look at another example, we're going to see that we have way different levels. We have a 26 CEC instead of a 5 CEC. And we have much higher levels of nutrients. Now, this pH is over 7, so this whole CEC number and the whole calculation method that's used in the labs, again, not the point of this conversation. I'm not training you in soil analysis interpretation to the nth degree, but I want you to be able to just look at this and understand when you look at this ammonium acetate extraction, which is what is most commonly used, that you're not getting the whole picture. If you look at the phosphorus, it's very low on the Bray 2, and because of the high pH, they also have an Olsen number, which is showing high. So we have high here, low here. What's this mean? Should we add more phosphorus? Do we have enough phosphorus? What about potassium? We have really high levels of potassium and magnesium. And maybe we should apply some calcium, you think. Or when you look at your manganese, you can see we're really low in our manganese. We have 5. That's just 2 points higher than the sandy soil. So we probably need to apply a bunch of manganese here. Well, if we go to the total nutrient digestion, we will see that our phosphorus, we have 715 parts per million in the reserves. So does it make sense to apply more phosphorus? Does it make sense to put out another 100 pounds of MAP? Does it make sense to put out more potassium? What about manganese? We have 254 parts per million of manganese in the soil, and only 5 parts per million were showing up in that regular soil analysis, which would have indicated that we should probably apply some manganese. So what does all of this mean in simple terms? What I want you to take away from this is if you have enough minerals in the soil, in the total reserves, even if it's deficient in your just common soil sample, you should focus on microbial health, on the soil health, on the organic matter, on the carbon level. Focus on the microbes because they are what will make those nutrients available and keep them in a plant available form. If you have low levels of minerals in your soil in the total nutrient assay, then you'll need to make soil amendments. And you may need to make some, you might even need some fertilizer. You need to think about the short term and the long term. Because if you want to get this soil sample up to the ideal levels all in one season, well, that's not really feasible. We need to be looking at 10 years, 20 years. I don't know, how long has it been since you added 10 years to your age or to your child's age and consider where you want your operation to be? How do you want your operation to be operating? What are the things that you hope to eliminate in 10 years? What are the things you hope to gain or accomplish in 10 years? And are the choices, the plans, your focus, is that aiming you in that direction? And this is one of those key things. If you have only 86 parts per million of potassium in your overall soil, well, that means you're going to always be depending on water-soluble potassium sources, which are very expensive. But what if you build a long-term plan into your budget of applying compost, of applying sources of potassium that are not soluble and are less expensive? You can apply higher volumes of potassium at a lower cost and build that overall system with the long term in mind. Replacement of nitrogen or removal rates and yield goals is an endless game. It's the more you apply, the more you're going to need later, whether that's later this season or later in your career of farming or later in your farm's career. If you apply excessive levels of nitrogen and you short circuit, putting on soluble nitrogen is somewhat like, let's use the example that you had a sugar factory and you're planning for the season. You're ramping up for the season to bring in all the raw ingredients and to build to manufacture, to process the sugars to fill all the orders for this year. And as you're doing that, someone somewhere decides that they are going to provide you with all the sugar that you will need for the whole year. And they bring you so much sugar, not raw ingredients, not things that you'll need to process, but so much sugar in its final product, if you will, or in a very soluble product, that it fills up your whole warehouse. It breaks some of your equipment, and you can't hold all of it. Like it's more than you can handle. And so sugar gets stored on the outside. It gets ruined, and then orders start coming in for sugar, and so you're really glad, and you start taking up all the sugars, and you make sure everybody has an extra pallet or two of sugars. And what happens? you run out and you're not able to supply and fulfill all the orders, and your whole factory has been broken because of this excess of sugars early season. So that analogy will probably break down somewhere along the line, and somebody can probably think of something that's not same as plants. But what I want you to think about is how the application of soluble nitrogen can have very, very significant impacts on the nitrogen fixing bacteria being able to provide nitrogen and cycle that free nitrogen from the atmosphere later in the season. So let's think about how do we get started? What do we do first? What do we do next? How do you take something from this and go from here and apply it to your operation? And part of my goal here is not to give you those answers, but to give you the questions to ask yourself so that you can look at your operation, understand it. You can partner up with Advancing Eco-Agriculture. You can partner up with the community of regenerative growers, people who have done this, who are walking in this way, and figure out what the right thing is for your operation, for you, for your family, for all the pieces that are involved, because it's a complex system. Nature is very, very complex, and we, as a part of stewarding nature, are also very complex, and our given scenarios are all different, and so it's a complex thing. And my goal here is not to give you a 1, 2, 3 recipe, but for you to start thinking about how these things apply on your operation. So think about cycles of life. Think about the carbon cycle. Think about the water cycle. Think about the nutrient cycle. We think about organic matter, but many times we don't think about it in the sense of a cycle. It's not something that we want there to be a static number. It needs to be cycling, much like the water. We don't want water to just be stagnant. Water needs to be cycling. Nutrients need to be cycling. So how does this look in each of these categories? When we think of carbon, well, organic matter, crop residue, stable humic substances, carbon. We think of microbial life. If we don't have microbes, it's going to be very, very difficult for that crop residue to break down and for all the carbon that's stored within that crop residue to become available for the next crop, for the nutrients to be released from that carbon, from that organic matter, so that the next crop is able to take it. When we think about microbes releasing that, we think about CO2 and photosynthesis. So if we have CO2 being released as these microbes are chewing, breaking down, working on this crop residue or this organic matter, they are releasing carbon dioxide, which goes up into the atmosphere. And if we don't have plants there that are actively photosynthesizing, that carbon dioxide will be lost up into the atmosphere and it won't cycle. If we have plants growing there that are photosynthesizing, and the more efficiently they are photosynthesizing, the more of that CO2 that's released can be captured by the plant, converted into glucose, or again, carbohydrates, a more simple carbon, and put back down into the soil. And so you see how the cycle works. We have crop residue, we have organic matter in varying stages of decomposition, and as the microbes work on that, CO2 is released, which is critical in the cycle of life, because if the plants don't have CO2, they cannot photosynthesize. And if plants can't photosynthesize, that means they can't give off oxygen. The byproduct of photosynthesis is oxygen. How many of you find oxygen quite important? I do. We need oxygen. So it's all about the cycle and keeping the cycle going. If we apply nitrogen early on, we could oxidize the carbon. And if we oxidize the carbon too early and there's no plants there, or if there's plants there but they don't have sufficient levels of nutrients for photosynthesis, then guess what? We're going to lose carbon dioxide and our organic matter levels are going to go down. And why is that important? Because of the water cycle. Organic matter is so important in the water cycle. When it rains or you irrigate, An acre inch is 27,000 gallons of water. And for every percent of organic matter that you have in your soil, you're going to be able to hold 1 to 1.2 points or inches, acre inches of water. So that means if you have an organic matter of 1, you can hold 27,000 gallons of water. If you have an organic matter of 2, you can hold 54,000 gallons of water, or 2 acre inches. If you have an organic matter of 3, you can hold 3 acre inches. So that suddenly makes a huge difference in our water cycle within our plants. You get a rain and you're capturing 100% of that water instead of most of it running off. So getting good infiltration is key. Because when we have good infiltration and we have a functioning carbon cycle, we now have a good water storage capacity, which means we have the ability to access that with deep-rooted plants and bring that moisture back up, percolation, and then evapotranspiration, and we get water back up into the atmosphere. Clouds form, and it rains. It's a beautiful cycle. It's a powerful cycle. And I believe the carbon cycle and the water cycle are so intertwined. And we have all these initiatives to affect the carbon cycle. And I think we need to bring the water cycle into that as well. The water cycle is very important. If you have a hard soil, if you have a hard pan, if you don't have good water infiltration, or if you burned off the organic matter, it's been oxidized through over-tillage or whatever it might be, which is why it's so great that there's so many people that are no-tilling, is because you are having less of that erosion. And oh my, erosion is another huge topic. You know, we talked about crop removal rates, and nutrients leaving through crops is really insignificant compared to the amount of nutrients that are leaving through water and wind erosion. And I continue to be shocked and embarrassed and grappling for answers as to how we are still losing so much soil to wind erosion. It's a real challenge. It's a real thing. And this is kind of off on a little tangent, but I really see lots of opportunities in really thinking outside the box. You know, we think about no-till and we think about all the different crops, but we're still thinking very much in a annual crop box. How about we start thinking about perennials? How about we think about trees and forests that are able to produce also food crops, but create additional evapotranspiration, create a deeper root system for a greater depth of water percolation. And therefore, it is my belief that we could effectively change the water cycle or the rain patterns in a very similar way that we have by taking the forests away. Enough for that rant. I think you get my point. What about the nutrient cycle? You know, we put on fertilizers. What do we think about when we think about fertilizer? When we think about nutrients that are critical for the plant's performance? So, nutrient cycle, crop uptake. So you've got the corn crop, wheat crop, cotton crop, whatever crop it is. Every plant, every leaf, every stem, every stalk has a certain level of nutrients within itself. And when we look at cover crops, this is a huge advantage for cover crops, or why cover crops are so beneficial is because of all this nutrient extraction that happens. And going back to the rhizophagy cycle and James White's teaching on that, which I would highly encourage anyone who's not familiar with it to really check that out. Because one of the things that will probably make you wrinkle your brow a bit and wonder what I'm talking about, but plants are some of the most effective nutrient cyclers. And I believe they are an interesting component in re-inoculating our microbial species. When you listen to James White and you think about endophytes within the seed and the rhizophagy cycle and how a seed wakes up and has all of those endophytes within itself and therefore inoculated on the plant, what if these plants in a big way are taking up nutrients because of the microbial colonization, but the signal for these plants to germinate is actually more on the microbial side and the microbial balance side. It's a thought that James put out there as a thought. I believe they're doing some research in that. But I've had so many experiences of growers who had weeds just take over, can't control them. I had one grower in Kansas who had a summer fallow of wheat, and if I'm not mistaken, it was water hemp that just completely took over. And he thought this was an organic field. He thought he was probably going to have to, take it out and spray it and take it out of organic. The next year that fall, they incorporated all of that biomass, and that was the cleanest wheat field, not only in his farm, but he said in the county. So what happened there? And let me just add to that example of an analysis that we did with plant sap analysis, where we sampled a tansy mustard plant, and we sampled, it was wheat, tansy mustard and wheat. And the wheat had 600 parts per million. No, I'm sorry. The wheat had 800 parts per million of calcium, and the tansy mustard had 6,000 parts per million of calcium. So now if you think about a tansy mustard crop at 6,000 parts per million of calcium, and you consider having a biomass of, say, 10 ton, you suddenly have a pretty high concentration of very bioavailable calcium. So just putting that out to say, nutrient cycling and the role that, well, we call them weeds, but they're really just plants that are growing that we didn't plan to have there or didn't plant there. And sometimes they need to be dealt with. I'm not suggesting that you just let every wheat, that's not what I'm saying, but just saying that there may be more of a purpose in these plants that grow prolifically than we sometimes think about. And this is where cover crops are so valuable. It's because you can put diversity in there. You can have microbial inoculation. You can have microbial diversity based on the plant species. And that's, my belief is, that's why it's so valuable to have these really, really diverse cover crop mixes. So, nutrient cycle, crop uptake, decomposition, microbial mineralization. If we don't have microbes, we can't mineralize what's in the crop, and we also can't mineralize what's in that reserve, if you will, those 900 parts per million of phosphorus and the thousands of parts per million of potassium. We need microbes to be able to mineralize that and make it available to the crop. So how can we most effectively get those cycles to engage and start complementing each other and building on each other if we find that one or all of them are not effectively functioning and working? And I think it's important that as growers, we're willing to look at what we're really seeing on operation. Is it as good as we think it is? We tend to think that we're pretty good farmers. I remember when I first was introduced to the bricks idea and the refractometer, and I thought I had really high quality tomatoes, and I tested the tomato itself, and I was like, oh, this isn't what I thought. And so sometimes we kind of have this idea about ourselves that we're pretty good, we're good farmers, the crops we're growing are really good, but when we start measuring, sometimes we realize, oh, well, we still have some things we can work on, and I find that to be quite true with the whole microbial or soil health aspect. We often think that we're in a better place than we really are. We start digging and we realize, oh, we've got some compaction problems, or oh, we've got some gas exchange problems. So here's some ideas on effective ways to get started Where's a good place to start? And I believe it's colonizing that root system immediately during germination. And why? Why is that so valuable? It's because in many crops, the yield is determined very, very early on. And if there's not a good microbial symbiosis going on and nutrient availability going on, the plant's going to think, better not put on as many kernels per head. Better not put on 2 ears. Better just keep it a bit easy this year, because in nature's way of thinking, if you will, it's looking to produce the best viable seed possible. So think of it from that aspect. The other thing is, these plants are usually most susceptible right in those early stages. So this picture that you're looking at of these barley plants that aren't even emerged yet, just look at the amount of root biomass that they've got going. Think about the amount of energy that is being packed into these little plants as they start germinating. And as soon as they emerge, they'll start sending sugars back down to feed these microbes. So this is a very effective way to kind of get that carbon cycle going. That's not extremely difficult. You don't need to make huge changes to move that needle in a positive direction, to get that cycle spinning just a little bit. Another example of a wheat plant that was treated with BioCode Gold. Just the amount of roots and the amount of colonization. So and if you're not familiar with looking at these roots, if you don't have microbial inoculation, the roots will be shiny and white. And I used to think that's a good thing. I was like, oh, these got really healthy roots, nice and white. But actually, the disease suppressive microbiome, the rhizosphere that is going to be most resistant to fusarium and verticillium and rhizoctonia, is going to be the one that's colonized like this. This is my recommendation. It's a product that John developed and has just worked really, really well, very consistently across the board. When you're planting cover crops, when you're planting your wheat, when you're planting corn, put BioCode Gold to it. It's diversity. You've got some bacteria, you've got some mycorrhizae, and it's very cost effective. And it works very, very consistently, season in, season out. So that's the one place you can start. Think about your fertilizer. Think about, what do my plants need when they're really, really small? Do they need 300 pounds of nitrogen? Does a corn plant this tall need 300 pounds of nitrogen? Or does my wheat plant need 50 pounds of nitrogen? Maybe just a shot of 5 pounds of a foliar urea, and we could look at the different forms of nitrogen as well. We're running out of time. We're going way over time. Let me just say, connect with someone on the AEA team. We'll be happy to look at your specific scenario and figure out what is the biggest limiting factor on your operation and where can you start. I like this quote from David Buffman, especially the last part where it says, in the school of nature, man must always be the pupil. He can never be the teacher. And I believe in the last century, we have tried to teach nature. We've expected nature to behave according to our guidelines. And I think we're seeing that it's a lot easier when we learn from nature. Nature teaches us diversity is crucial. It wants the soil covered with living plants. If we destroy nature, it will destroy us. It teaches us that there is abundance of life if we're willing to share, care, and participate. We're a part of this natural system, and with a greater ability as humans to build or destroy than any other species. So be curious. See what you're looking at. Make sure that you know what your goal is. Minimum 5 years. Think about why you're farming. Why is it that you do what you do? Is it the right career? Is it the right occupation for you? I think most people will say, yes, I can't imagine not doing it. And I've heard so many people, I couldn't count them on 2 hands. Probably hundreds of people that said, farming is fun again. I can finally make my own decisions. I understand what I'm doing. They've become a part. They've become a steward again. They're not just being farmed by fertilizer companies. So make sure you know what your goal is. Determine where you are now. Which direction are you heading? Is it the direction you want to be and where you want to be in 5 years from now? And if you're off course, just start making corrections. It can be very dramatic, make huge changes, or it can just be a couple small things. And you start shifting the way you're stewarding your operation. If you find yourself in emergency, like at the brink of bankruptcy, or like my crop failure after crop failure after crop failure, which by the way is what started this whole company. John got frustrated with having 3 crop failures in a row. He told his dad, we might as well do nothing for nothing instead of doing all this work for nothing. So if you find yourself in that place, don't panic. Stop, look, see, listen. Reach out to people. There's many people. And there's people that we have started working with that were there. And they're pulling through. There's hope. There really is hope. See what's going underneath the soil. This picture is always so inspiring to me. Thinking about water percolation. Think about the crops that you're planting, especially if you're planting cover crops. This picture is of old prairie grass, or it's wheat. It's like one of the ancient varieties of wheat. And just look at how deep those roots are going. Now think about the amount of moisture, of water that it's going to be able to draw back up. Think about the carbon cycling and the depth of the carbon cycling. Think about so many things that are benefited when we have this deep root. Think about as compared to this, where we just have, we might get the top 10 inches if we're lucky. So consider what crop species that you're mixing. Get some deep-rooted plants out there. Health, whether it's soil health or human health, is a progression. I like to think of health as you're either above the sick line or below the sick line. And there's many people that are, and many soils that are on the sick line or below the sick line. They're not dead. They're headed that way. And that's something we can change. Simple changes. We become healthier. So we're here to make a difference. Advancing Eco-Agriculture is a team of consultants, a manufacturing company that manufactures plant nutrition products. And we understand these products in the toolbox. We understand agriculture systems inside and out. And we're here to make a difference in the food that's grown. That is my personal passion and my personal mission, that more food can be produced that has less toxic chemistry on it and more nutrition. So if you're serious about making a change, you want to get started, give us a call. We're here to help in whatever way we can. So with that, McCain, back to you. We'll have some questions, if there are any.
Yeah, it looks like we had almost more of a comment to start out. I don't know if David, if you can see that there, if you pop up that Q&A portal.
Yep, got it.
Not sure if you have any response to that comment that came through there.
Just read that. P205, because back in the day, the most accurate way to analyze P content was and still is by combustion oxidation. Hence the combustion product, regardless of the P species, PO4 is diphosphorus pentoxide. Yes, totally agree. And they just didn't change that on the label to specifically say, oh, it's phosphorus, you're getting X% phosphorus, like they did for the nitrogen. It's great.
All right, so that's all that came in. If anyone has a question, feel free to get it in real quick. Otherwise, if you think of something else later down the road, you can always reach out, as David said, to AEA directly, or you can also, of course, always reach out to us at No-Till Farmer, and we'll make sure that we get your questions answered, get them to the right folks, and get an answer for you. So, looks like we got another question here. Benjamin says, how does chicken manure help?
Great question. Chicken manure can provide you with nitrogen, with phosphorus, and with potassium, and is a good source of those because it's not as soluble as your other sources of soluble phosphorus. It is still helpful if you're able to convert those nitrogen the nitrogen component as it's breaking down. If you can convert that into a protein form of nitrogen, there's definitely benefits to that. But again, I will say that if you already have sufficient levels of potassium and phosphorus in your soil, then you would be applying the chicken litter for the nitrogen source if you don't have that nitrogen cycle functioning in your crop. If you don't have good gas exchange, if you don't have the ability to fix enough nitrogen for the crop, chicken litter is definitely a good option for providing some of those materials, and can be a good consideration to build potassium and phosphorus levels, especially if you have a source that's more economical than say potassium sulfate or sulfomag or K-mag. You may consider. I would definitely consider that as a good option for potassium and phosphorus soil amendment, where you put on a consistent amount and you build up those potassium phosphorus levels over time.
All right, looks like we got a couple more come in here. So someone's wondering how you consider the role of humics and fulvics in today's agriculture. Same benefit in getting more microbes in the soil if we apply.
That's a really good question. So when you think about humic acid and fulvic acid, and maybe if you're applying it, most of the humics and the fulvics today are in the form of humic acid and fulvic acid. And if you remember the comment I made on the phosphorus, how phosphorus is manufactured, or the phosphorus fertilizers that we have go through a process of chemistry reaction where the calcium and many of the micronutrients are stripped away from the phosphorus to give you a higher phosphorus number. And the same thing happens with the humic and the fulvics today. So they start out with humulite or with leonardite ore. There's various different deposits of humates in North America, and the extraction process extracts and denatures the humic and the fulvic as it occurs in nature, and those processes will actually discard. They'll not use the humin fraction or the actual portion of that original ore or that raw ore that has the anion holding capacity. So yes, humic acid is good, fulvic acid is good, but what we prefer and what has worked really well is when you have the humicarb is a micronized humate, so you have the humic acid and the fulvic acid, which gives you, and you have the humin fraction in there, so you have the anion exchange capacity and you have the cation exchange capacity. So definitely plays a role and plays a key role in. We also find that when you have these extractions, there tends to be, depending how they're put together, and I this is very much in generalities, but there tends to be less of a microbial stimulation because of that extraction process. In other words, the product is denatured. It's not something that nature recognizes. It's not in its holistic form. So that's why we prefer to, that's why John developed Humicarb, and it has been very, very effective in stabilizing soluble nitrogen and phosphorus compounds, which for any growers that we work with in the transition, that's a step number one, is to stabilize any soluble nitrogen and potassium applications with the Humicarb, so that you don't leach and it doesn't flood your crop in the root zone and affect the. You could think of it, going back to my sugar analogy, you could almost think of it as additional warehouses to hold the sugar so that you don't destroy the manufacturing facility.
All right, they're pouring in now, so I guess we'll try and get a couple more here before we sign off, just real quickly. Right. I've been planting cover crops for a number of years now. Could this be the reason I didn't have water hemp in my soybeans this year?
Yes, maybe very possible, especially if you have, if you have better soil tilth, if you have better nutrient availability and that specific nutrient that the water hemp was there to extract. Yes, quite possibly.
All right, and then does AEA offer any treated seed products?
treated seed products or seed treatment products. The BioCode Gold is a seed treatment product. So that's a dry product that we put on dust on the seed, and we're playing around with actually treating the seeds with various mineral components. So some people aren't set up to put a liquid into, say, their wheat, and we've had some pretty interesting results with dryland wheat and cotton of treating the seed with a micronutrient mix and then putting the BioCode Gold to that. So if you want to know more details on that, we can just reach out and we'll be happy to share that with you.
All right. And then do you have a book or resource recommendation to learn more about the soil in a regenerative manner?
Yes, good question. John has done a bunch of podcasts, and those podcasts are put into a book called Quality Agriculture. That's one that I would definitely recommend. Just great conversations with many people who are leaders in this regenerative space. Yeah, I think that's a good start, and that'll get you. I think actually John has on his podcast, he has a book list that he recommends. There's a lot of books.
All right, and we'll just do one more here. Question is, could you comment on the use of a small amount of fertilizer, PK, etc., applied in the fall at a depth of about 7 inches? Of course, the grower will use GPS to plant over the fertilizer band in the spring.
Great question. So I would, to that question, I would, if the grower has sufficient levels of potassium and phosphorus in the soil reserves, you will be dollars ahead by putting biology in that zone, putting microbes in that zone, and those microbes are going to be working throughout the whole winter. They never stop. The ground can freeze solid, and you'll still have some microbial digestion going on. That's why when you have first cutting hay, it's always way better than second, third, and fourth cutting, is because you have all of those nutrient reserves available. So if you need a soil amendment, like if you don't have enough phosphorus and potassium in your total soil reserves, like let's say you have a very sandy soil, yes, that would be a very efficient way to put it out. But putting it out in the fall, especially phosphorus, it's all going to be tied up. Typically, you have a couple days to maybe 3 weeks at the most for your plant to take up phosphorus. So I would not put out phosphorus or nitrogen in the fall. Potassium's pretty stable. You could probably put that out, but it's not. That's the other thing. You can easily supply the plants with potassium in the season. Potassium's like candy to the crop. So it'll just soak it up.
All right. Well, thanks everyone for those great questions. Thanks, David, for the thorough answers. And then just a reminder that today's presentation and the audio, it's all going to be made available at no-tillfarmer.com. If you'd like to review it or share it with somebody. Also, as I said at the beginning, in case you missed it, you'll receive a link in your email within 48 hours of the conclusion today. So watch out for that. And then just like to say on behalf of Advancing Eco Ag and No-Till Farmer, thanks for joining us today. And always feel free to reach out to us if you have suggestions for other topics you'd like to see us cover. So with that, thanks very much. And I hope you all have a great day.